Hello students, welcome to this lesson. This lesson is on linear programming, that is chapter 12 in your mathematics second volume. This is the first lesson. Before starting the lesson, let me tell you one thing. Before starting to study this lesson, you should know what is linear inequality and how to draw the graph of linear inequalities. This you have done last year, first PUC, that is 11th class. So there is a chapter, linear inequation or linear inequalities. There you have studied what is the meaning of inequality and how to draw the graph of linear inequalities in coordinate plane, that is xy, where there are two variables, and also how to find the solution plane using a testing point. So these are the things we have studied. Therefore, before starting this lesson, first you should revise linear inequality of the 11th class or first PUC. Let us start. So let us try to understand what is the meaning of LPP. In short, it is called LPP or linear programming problem. Let us consider one simple example. Say a furniture dealer deals with two types of furnitures. Let us say chairs and tables only. See, he has 50,000 rupees to invest and storage space for at most 60 pieces. That means he can store altogether 60 chairs and tables in his storeroom. Then he has these are the things. Cost of one table is 2500 and cost of one chair is 500 rupees. So these are the informations given. Now profit of one table is 250 rupees and profit from one chair is 75 rupees. So these five informations are given to us. Now the problem is this: how many chairs and tables he should have to get maximum profit? So this is the problem. With 50,000 rupees investment, 60 pieces which he can accommodate in his storeroom, with the profit of 250 rupees for one table and profit of 75 rupees for one chair, and also cost of one table 2500, cost of one chair rupees 500. How he has to purchase a number of chairs and tables so that his profit will be maximum without violating any of these conditions. So that is very important. Now there are different possibilities. Let us see. Say case 1 is, suppose it is extreme case, only tables he is purchasing. Let us say then number of tables which he can purchase is 50,000 rupees. That is the total amount available, and one table costs 2,500. Therefore 20, maximum 20 tables he can purchase. Now what is the profit with this one? So 5,000 rupees. Similarly, let us take another case. So only chairs, then number of chairs will be 50,000 divided by 500. So that is 100 chairs he can purchase. But this is not possible because there is a problem. The storeroom can accommodate only 60 pieces, whether it is table or chair. So but here it is 100. So this is one problem. So he can purchase only 60 chairs. Therefore, suppose he purchase only 60 chairs, then profit will be, in case he is able to sell them, that is also very important, then it is 4,500 rupees. So there is a difference. So profit in one case it is 5,000, in another case it is 4,500. Now what are the problems if we take these two extreme cases? See, one is, in the first case, his decision will not allow to use the storage capacity fully. See, he is purchasing only 20 tables. That means he is unnecessarily investing amount on storage, that is storeroom. So definitely storeroom also involves rent and other things. So that means it is underutilized. This is one problem. Second one is, in the second case, his decision will not allow to utilize the money available for investment. See, because of this storage problem, he can purchase only 60 chairs. That means he is investing only 4,500 rupees, whereas he is 50,000 rupees. Total amount will be total amount available is 50,000 rupees, but that much amount he cannot invest. That means dead investment. So amount is not utilized. One is underutilization of space, another one is underutilization of amount. So these are the two problems. Then also the profit is less, you can see. So problem is to find now, therefore now you can't do it by trial and error, say one chair and say 59 table, not like that. 59 table not possible also, because maximum table itself is 20. Therefore you have to now manipulate. So the problem is to find number of chairs and tables he should purchase to make maximum profit. Now the question is there any mathematical method of helping him to say that you purchase these many tables and these many chairs which will give you maximum profit? Of course, condition is that he should be able to sell all the articles which he purchases. So that is the understanding. So without violating the constraint, that is very important, without violating the constraint, that is storage as well as investment amount. So without this one, if he can do it, this problem can be tackled using a concept called LPP, linear programming problem, which is a branch of mathematics. Let us study this. It's a very interesting case. So the problem of the furniture dealer is this. Let us take like this, because we are students of mathematics. Always you can use algebra and other unknown variable, etc. Therefore let us start like this. Say the number of table is x and number of chair is y. Now int and profit will be equal to z, let me call it as z function, 250x, because profit is 250 from table and 75 rupees from chair. Therefore it is totally 250x plus 75y. This is one thing. What are the conditions we have to mathematically look into? First one is 2500x plus 500y should be less than or equal to 50,000, because total amount available is 50,000 only. It cannot exceed this. Second one is, so this is investment constraint. Second one is x plus y should be less than or equal to 60, because total number of articles should be less than or equal to 60. So this is called storage constraints. Constraint means condition, restriction. X of course should be more than 0, y also should be more than or equal to 0. This is called non-negative constraints. So these are the mathematical concepts. So we can say now z equal to 250x plus 75y, which is to be maximized, that is also called optimized, is called objective function. This is called objective function. Then the conditions 2500x plus 500y less than or equal to 50,000, then x plus y less than or equal to 60, then x more than or equal to 0, y more than or equal to 0 are called constraints. They are called constraints. What is LPP therefore? Linear programming problem. This is definition can be given like, now we have understood what is the meaning of LPP. We can give the definition like this. A linear programming problem is a problem which calls for optimizing. Optimizing means maximizing or minimizing a linear function of variable called objective function, subject to a set of linear equations or linear inequalities. So this is called linear inequalities are called constraints. So this is the definition of linear programming problem. Let me repeat. A linear programming problem is a problem which calls for optimizing, meaning maximizing or minimizing a linear function of variable called objective function, subject to a set of linear equations or linear inequalities. They are called the constraints. So this is the definition. Now we can formulate furniture dealer's problem as LPP, which can be expressed as follows. Now we can exactly formulate what is LPP for this particular problem. Let us say number of table equal to x, number of chair equal to y, then maximize z equal to 250x plus 75y, subject to, this is the tradition of writing the problem, 2500x plus 500y less than or equal to 50,000, then x plus y less than or equal to 60. Then of course this we have to write x more than or equal to 0, y more than or equal to 0. They are called non-negative constraints. So this is the structure of LPP. Let me sum up here at this stage. So what you have to do is, whatever problem you want to solve, the variables which you have to find, that the value for which you have to find the variable for which you have to find the value, those things you should take as x and y or whatever. Then maximize or minimize. Which is to be maximized? Profit means maximize. Suppose it is a cost, you have to minimize. So that is called objective function, that you have to write first. Then subject to the constraints. Constraints you have to write. So this is the structure of LPP. Definition. There are some terms associated with LPP. Let us clarify those things. First one, a problem which seeks to maximize or minimize a linear function subject to constraints as determined by the set of linear inequality is called an optimization problem. This is one definition. Second definition is the linear inequalities or equations or restrictions on the variables of a LPP are called constraints. Subject to those things are called constraints. Next one, linear function z equal to ax plus by, where a and b are constants, which has to be either maximized or minimized. That is called objective function. Z there it is called objective function. These are the terms. Then the next one, any point on the feasible region that gives optimal value, that is maximum or minimum, that is of the objective function, is called optimal solution or feasible solution. About this one let us see later. So these are the basic terms involved in the LPP. Now LPP consisting of the following. This is the, once again, let me just sum up. Structure is like this: objective function z, then constraint. For example, you can write like this: z equal to maximize or minimize, z equal to ax plus by, then subject to. For example, there may be linear inequality of any number. Of course, last you have to write x more than or equal to 0, y more than or equal to 0, or it can be the other way also. It can be less than or equal to, or it can be more than or equal to also. Sometimes it can be combination also. Some of the linear constraints may be linear inequality involving less than or equal to. Some may be more than or equal to. So this is the structure of the LPP. Now next question is how to find the maximum and minimum value. So this is the next question. So what you have to do is draw the graph of the linear inequalities. Z you have to keep as it is. Only linear inequality, that is subject to constraints. Those constraints you have to draw. So for example, here you see one constraint is 2500x plus 500y less than or equal to 50,000. Second constraint is x plus y less than or equal to 60. Of course, other two are non-negative constraints. So you have to draw the graph like this. So now see, this is the feasible region. In the definition it has come. This is called feasible. That means solution set consists of this one. So now one is 0, another one is A, another one is B, another one is C. So these are called the corner points. See, feasible region means it is the region where you have to find the solution or solution lies there, and these are the corner points. And the maximum value of z is attained at the corner point. This is very, very important concept. So what you have to do is first formulate the problem, then draw the graph of linear constraints only. Objective function you have to keep as it is. Then you will get corner points like this. You get a feasible region by shading them because they are all linear inequality. You know how to shade them. Then you get a convex actually polygon, and then you have to identify the corner point. Now at this point what you have to do is put the value in z. Whichever is maximum z, that is the solution for the LPP. So this is the method actually. Now theorem 1. So there are theorems which help us to do this one. This is the first theorem. See, let R be the feasible region, convex polygon, which we have seen in the previous stage, for a linear programming problem, and z equal to ax plus by be the objective function. When z has a optimal value, that is maximum or minimum, where the variable x and y are subject to constraints described by linear inequality, this optimal value must occur at the corner point. Therefore, we have to draw the graph, identify the corner point. So this is the first thing. Feasible region. Say this is the thing. See, we get this type of graph. See, A, B, C, D. These are the four corner points. Based on the number of constraints, it can be polygon of any sides. So it can be 6 sides also. So in that case, you will get 6 corner points. Sometimes you get 2 corner points, 3 corner, not 2, 3 corner point, 4 corner point, like that. all these corner points are the points where the maximum of z occurs and minimum also, both maximum as well as minimum. So that is why this theorem helps us to understand the find the solution. So this is the second one. Both theorems are on the same. Let R be the feasible region, convex polygon, for a linear programming problem, and let z equal to ax plus by be the objective function. If R is bounded, then the objective function z has both maximum and minimum value on R, and each of these occurs at the corner point. This is very important. Because of this theorem, we are able to find what is maximum or what is minimum. Now LPP, let us take once again this furniture. Let us solve the problem for him first, then we shall work out the mean. Consider z equal to 250x plus 75y. This is the objective function. Now subject to these things, so these are the constraints: 2500x plus 500y less than or equal to 50,000, x plus y less than or equal to 60. Non-negative constraint, it is a tradition, we have to write x is more than or equal to 0, y is more than or equal to. Now this can be written as 5x plus y equal to 100 and x plus y equal to 60. So you can cancel the common thing, so that graph will be easy. So now you draw the graph. I have shown the graph now directly. So first you draw the graph of the first linear equation, graph of the second linear equation. Then you know how to find the inequality graph. So shaded region is the feasible region. Now you can see here in the graph, corner points are, one is 0 0, second one is 6 0, third one is 10 50, 0 60, then 10 50, then C is 20 0. These are the four corner points, and the theorem says maximum and minimum value occur at the corner point only. Therefore what you have to do is, we have to just take the corner point. So corner points are 0 0, B 0 60, D 10 50, C 20. Now there you have to substitute in the objective function these values. So that is what I have done. Now you can see where maximum occurs. Maximum occurs at the point D. Therefore that is our problem, the solution for the problem. Meaning, what is 10 there? 10 indicates the number of tables, and 50 indicates the number of chairs. Therefore now the solution is this: number of tables must be 10, number of chairs must be 50, and the maximum profit is 6,250. It is not 5,000 or 4,500. It is 6,200 without violating the conditions. For example, you see, now you can check. So storage space is for 60 and he is utilizing 60. And total amount also you can check how much amount he has to invest. It is not exceeding 6,000 because both should be satisfied. Now therefore the furniture dealer should purchase 10 tables and 50 chairs to maximize the profit. So this is the idea. Now let us take exercise basic problems in the beginning. Solve the following linear programming problem graphically. See, already problem is given, so it is not word problem. The LPP directly is given. Our job is to just draw the graph and find the maximum and minimum as the case may be. See, here the question is maximize z equal to 3x plus 4y. That is the objective function subject to the constraint. First constraint is x plus y less than or equal to 4. Second one is non-negative, x is more than 0, y is more than or equal to 0. Therefore there is only one constraint. It is very simple linear programming problem. So what you have to do is just draw the graph like this. Now you know how to find the feasible solution. Just draw, because it should be less than. Therefore this is the feasible region. Now what are the corner points? You can see here corner points are, one is 0 0, another one is A40, another one is B04. Now check. So this is the step in all the LPP. Corner point you have to make a table, then those values you have to substitute in the objective function z. Now it is very clear, maximum value is obtained at the point B04. So 16 is the maximum value and minimum value is of course 0. So this is the first question in the exercise. So you can see here. So maximum is attained at 04 and maximum is 16. Next, solve the following. This is the second question. See here, minimize. See, either it is maximize or minimize. Minus 3x plus 4y subject to first constraint x plus 2y less than or equal to 8. Second constraint 3x plus 2y less than or equal to 12. X is more than or equal to 0. Y is more than or equal to 0. Therefore, the solution should be like this. So first you have to write the given LPP like this. Now you draw the graph. See, when you draw the first graph, you get like this. That is x plus 2y less than or equal to 8. That is one straight line. And 3x plus 2y less than or equal to 12, second straight line. Then shade the feasible region. So you can see here the point. So like this. This is the feasible region. Now what you have to do is corner points you have to find. So one is O, second one is P04, third one is Q23, fourth one is R40. See here there are 4 points. So it is a quadrilateral. And next one is corner point. You have to take a table, make a table, then substitute these corner point values in the objective function z equal to minus 3x plus 4y. Calculate the value. Now you can see here very well. Question is minimize. So minimum value is obtained here. Then you have to write it. Minimum is attained at 0.4 and the minimum value is minus 12. This is the second question. Next, solve the following linear programming problem graphically. See, third question. Minimize, once again it is minimize 5x plus 3y subject to, there are two constraints, 3x plus 5y less than or equal to 15, then 5x plus 2y less than or equal to 10. Of course, non-negative constraint is always there. So this is the structure, this you have to write first, then draw the graph as before. Every time you have to draw the straight line and then find the feasible region. See here, you can see this is the feasible region. Corner points once again 0, 0, 0, 3, then 20, 19 and 45, 19 and A 2, 0. If the graph is perfect, then even you need not solve it. Otherwise, P point you have to solve actually algebraically, then you have to locate it. Now these are the corner points, so check. So 1, 2, 3, 4. So 0, 0, B and P. So here maximum is Z is attained at 20, 19 and 20 by 19 and 40 by 19. So you can check it. In anything, whenever you get the corner point, at that corner point you have to check, that's all. Next one, solve the following. See, sixth question, minimize z equal to x plus 2y subject to 2x plus y more than or equal to 3, x plus 2y more than or equal to 6. So this is a question where it is more than inequality is there. So this is the given thing. So draw the graph first. See like this. Now you have to shade the region. So it is more than, therefore the graph is like this. Like this. And second one is like this. Now it is very clear. Corner points you can identify. One is B03. Another one is A60, only two corner points. Therefore, you have to find corner point B03, A60. So 66, both are giving the same value. So this is important. Minimum is attained at all points on the line x plus 2y. You can check it here. Even so, it has got many solutions. Therefore, you can take the entire line. Everywhere it, of course, condition is x should be more than 0, y should be more than or equal to 0, and any other point on the line is obtained. This is very important. Then this is unbounded because it's not bounded region, unbounded region. So this is an example. Next one, solve the following linear programming problem. All the examples which I have taken today, they are not word problems. LPP is directly given. What we have done is we are just drawing the graph, finding the corner points and then testing the objective function by substituting those values and finding maximum minimum. So maximize z equal to minus x plus 2y subject to these conditions. So here there are three constraints actually. One is x plus y more than or equal to 5, x plus 2y more than or equal to 6. Another one is there, x is more than or equal to 3. Not x is more than 0, but x is more than or equal to 3. So first you have to draw like this. all the linear constraints you have to draw. Then first find the, so these are the values. Now find the feasible region by shading the graph. This is very important, like this and like this. So this is the, now it is very clear once you draw this one. See, corner points are, you can see here, one is P, that is the corner point, second one is Q, that is the corner point, third one is A, only 3, P, Q, A, these are the corner points. Now you have to check here, A, P41, Q32 and A04, and it is maximized, so maximum is 6, so Z has no maximum value, because you see here what happens is, if you keep on taking different values, because it is unbounded, Z unbounded, so it keeps on increasing A, because A you go in this direction, because the corner point is this one, but since it's unbounded, so this has no, so feasible region is unbounded, so therefore sometimes what happens, it has minimum but it has no maximum subject to this condition. So this is the problem with this type of question, unbounded region. Summary. Now let us summarize. We have taken sufficient number of problems. Steps of LPP: convert the given word problem into the following, that is Z equal to, depending on the problem, maximize or minimize AX plus B. For example, a problem of furniture dealer, so that type of problem. Then subject to, this you have to write like this. Then the second one is draw the graph of the constraints, that is linear inequality. Locate the corner point, this is the third step, like this. Then what you have to do is substitute the corner point in Z equal to Ax plus By, find the maximum or minimum, whichever is the case. If it is maximum, maximum you have to find, minimum, minimum you have to find. So this is the summary actually. Therefore you have to remember like this. Today's class I have taken only the graphical method. I have not taken word problem. So only just to acquaint ourselves with the method of solving. Different types of linear programming problems are there. Say for example, one is manufacturing, and we are going to study all these things in the next class onwards. In this problem, we determine the number of units of different products which should be produced and sold by a firm when such product requires fixed manpower, machine hours, labor hours per unit product, etc. All these things. This is called manufacturing problem. We have many such questions. For example, a factory produces say 2 types of computers. Then what should be the number of computers should be produced, etc. Similarly, diet problem. Sometimes you have to mix different types of grains, food grains, etc. ingredients to prepare one particular food. So there sometimes minimize the cost. They will give the conditions. So these many nutrients per each unit. This much nutrient must be there, like that. So such problems are called diet problems. We have many such interesting questions. So that is called diet problem. Transportation problem means actually, for example, there are in this problem we determine the transportation schedule in order to find the cheapest way of transport product. There are many interesting questions. This is involved in related to passengers, or sometimes it is, there may be goods carrier which has to shift the materials or products which are prepared by one industry or factory, and they have to shift it to some other place. All such problems, they are called transportation problem. These are the major problems which we can solve using LPP. So these are the major category. Of course, this can be applied in many other situations. What we study now, because it is the beginning, we consider these types of problems. Thank you for watching this video. I hope you will definitely appreciate this one. And I will be continuing this lesson. That is, I will be taking the examples of this type, that is diet problem, manufacture problem, transportation problem. And first we shall formulate the LPP, then draw the graph, and then find the feasible solution, that is optimal solution, value for Z, X and Y. So please subscribe if you have not yet subscribed, and share with your friends, as I already requested in many of my previous lessons. I am happy that students are watching the lessons. My request is, whenever you watch this type of lesson, first you must revise the first PUC topic which is related to this, so that it is easy, because I cannot once again start with those things. It will be entirely waste of time for you also. So whenever you watch this lesson, this type of lesson, first you have to prepare, revise the content necessary for this topic, then definitely you will appreciate it. Let us meet again in the next lesson, that is problems I will be taking from different areas like diet problem, manufacturing problem, etc. Then we shall find the solution. Until then, bye, take care.